Is there anyone that doesn't know what Slido is today? I guess not. Okay, cool. I did my job well, I guess, today. So you're good to go? Okay, so on my left, we have Zoe.
Yes. Weil.
Weil. Yes, this is my... So I'm going to let her present herself because she has it already on her slide. And I wish you an enjoyable talk.
No worries. Thank you. That is a very nice welcome. Waiting for my water, so pardon. Today we'll be talking about tree-structured recurrent neural networks as a tool for learning from human code. I will start with a disclaimer that some pieces of this presentation assume some prior familiarity with neural network architecture. Sorry. You know what? I might end up having to do this on my laptop. Jesus. This is not good. That's good to know. All right. Actually, yeah, it's not too bad. You're right. Because I'm able to... Okay, no, I'm not. Not bad. All right, so this is the obligatory About Me slide. My name is Zoe. I write for a blog called Mindful Machines, and during my free time with my very good friend Marcin Mayron, who actually happens to be Polish but is not here today, unfortunately. My day job is as a chief scientist of AI at a healthcare AI company at Resulta Health. Sorry, called Resulta Health. And we help bring value-based care to Americans. So there's that. All right. Since we're talking about using RNNs to kind of better understand code, it would be helpful to start with looking at some of the existing tooling in, the Scala ecosystem. So here's a list of, some of many of them, and I've used, I think, actually all of these myself, and they're wonderful. There's many more of them, but these are quite wonderful. And what they all have in common, however, is that they're all rule-based, right? And there's nothing really wrong with that, with having rule-based tools. But it does make a certain assumption that code is nothing really more than a set of syntactic rules. Again, nothing wrong with that assumption, except I happen to think, and I think many of you will agree with me, especially in practice, that there is code is often more than just code, right? There's fundamentally a human element attached to code, as well as a time component, right? So any bit of code and infrastructure will have a personal style attached to it, and it will include the personality of the person who wrote it. Are you more organized or are you more loose? Are you spontaneous or are you more controlled in how you go about problem solving, etc.? And all these things manifest themselves when you go from problem solving to actually implementing your solution. It'll also vary based on your engineering background, right? So an API engineer will probably write vastly different code compared to a full stack AI engineer, a front-end engineer, etc. What brings this human component together, however, is this element of time, right? And I think nowhere is time better, and its impact on code is better manifested than when you go through releases, right? Even like releases of one library, several releases of one library may vary a lot in terms of style, right? New release, many things get changed, including, incorporating the styles of the new engineers, or even the same engineers who have learned more about, their specific craft since the prior release. So we want to be able to learn from that, right? And that's what this talk is really about. So what can we learn, right? There are all these nuances, if you will, and we want to be able to use them to take, you know, coding and our experience with code to the next level. So one of the first things that we can learn from is, you know, to better understand human interaction with code. And, you know, this is really key because how you go about problem solving is so important, right? You want to be able to better understand not just your colleagues, whether it's at work or on an open source library, but you want to see how, and you should be able to see how they came to make the decisions that they did, right? So their thought process, if you will. And in this way, code is really like a natural living document. You should also be able to, another thing we can learn from this process is to sketch and compose higher level programs and architectures, right? So you might be sitting around and you want to quickly talk, you know, in English or whatever language that's not, you know, coding, about, you know, how you would go about solving a problem, and you want to quickly have something that generates some pseudocode about that, you know, outlines your solution, perhaps. But this last bit, I think, is what you will all probably, you know, sympathize with the most, which is, especially those of you who have ever worked at a company that's been around for longer than 5 years, right? Which is the need to understand deep, complex architectures, dependencies, and code bases, right? And this is both a daunting task, but it's also wholly unavoidable. And, you know, if you're a new member of the team, you know, this is a really enormous undertaking. In fact, it takes engineers, you know, 2-3 months on the easy side to get acclimated to new code bases. And we can ease that process if we're able to see kind of the outline of it and the thought process that went into building this final product and code base. As it turns out, this this talk and this endeavor, if you will, comes at a perfect timing. Just days ago, I hadn't even finished putting this presentation together, that GitHub released a data set of code challenging folks to innovate. And this has a lot of resemblance to challenges that we saw at the start of the image rec boom a couple of years ago, as a result of which a lot of innovation was made in the image rec space, right? People knowing that we're at the edge of something really great, and putting data sets out there and encouraging people to innovate, collaborate, etc. So this is kind of like a now or never moment, opportunity for us to seize. So how can we learn, right? Now, the key to learning is representation, right? Whether you're a computer or a person, you know, that doesn't really matter. Even if you want to learn a new language, let's say, right? One of the first things that you'll probably learn is how to represent and write, you know, ideas and words in that language via the alphabet and its syntactic structure. But that's not enough. You actually also have to be able to reconstruct new ideas and be able to synthesize information in this new language that you want to learn. So with that being said, you know, this movement from representation to reconstruction actually refers to a specific class of algorithms in deep learning called autoencoders. And in this architecture, you move from the original high-dimensional data to a sparse representation of it. So I want to use my pointer here to illustrate, but I'm afraid it'll mess up the presentation again. But basically, all the way on the left-hand side, you see the original input in higher dimension, and you end up with some lower dimension reconstruction of that. In any case, specifically for this project, we used one of the two variants of autoencoders called the denoising autoencoder. There's also the variational autoencoder, which we didn't use because, quite frankly, we couldn't afford to do so, because it introduces a certain variety in code that you can't really afford, right? Code must be exact in its representation to be compilable. Great. So let's kick off digging into the representation bit and really understanding how we can, represent code in a way that the machine will be able to understand. Because we talked about representation at a high level, but we're digging in deeper with each slide. So encoding is typically what's used to represent real-world concepts in a format that is understandable by a machine. And what we want to do right now is kind of an exercise in thinking about, well, how would we do that representation, right, when creating this library and platform. So first things first, the question you have to ask yourself is, well, what does the data look like, right? So let's look at the data. This is a piece of code, right, much like any other bit of Scala code. And what are some of the characteristics we see here, right? First of all, it has structure. It's a bit of structured data. It's also sequential. Order here matters. And finally, and this is key, as demonstrated by a doodle that I did of the scalameta ASTs, it's also hierarchical. And that's very key in us building this model and product and solution out. So starting with structured data, we have bag of words models, but they assume that pieces of code are independent of each other, which really they're not. And then there are sequence models, which construct concepts and logical representations as an order-sensitive function of a sequence of tokens. But then there are also tree-structured models, which compose each logical expression from its constituent subcomponents according to a given syntactic structure. So, order-insensitive models are insufficient to fully capture the semantics of natural language due to their inability to account for differences in meaning as a result of differences in word order or syntactic structure. So, as far as our options are concerned, that really left us with either order-sensitive sequential models or tree-structured models. So first we're going to explore the first two characteristics and try to handle the first two characteristics of our data, which is structured and sequential. I think that green graph there is able to illustrate that quite well, right? So it's sequential. It happens over time, over a given time period, code develops. Obviously not taking into account the hierarchical structure of it also. Now, recurrent neural networks as a class of models in deep learning have been proven to be particularly good at modeling this kind of data, this kind of sequential data over time, because they consider the current input in addition to previous input. And they also have internal memory. This is roughly what a vanilla recurrent neural network looks like, where you have the hidden layer, you have the hyperbolic tangent, which is the nonlinearity function, and then you have W, the parameter matrix at layer L. And you want to look at the hidden states from the previous layer, current time step, and the previous time step, the current layer. Unfortunately, backpropagation dynamics in vanilla RNNs cause the gradient vector to grow or decay exponentially over long sequences. This is commonly referred to as the exploding or and also vanishing gradient problem. And it makes it difficult for the recurrent neural network model to learn long-distance correlations in a sequence, which is a huge problem for us, given the task at hand, right? We said there's a huge time component, particularly in the case of large code bases, and we need to be able to learn from that. So the first issue, the one of exploding gradients, is actually fixed with a heuristic of clipping the gradients at some maximum value. The second problem, however, of vanishing gradients is a bit more tricky, but it can be mitigated by using a memory vector in addition to a hidden state vector. And this is where we see this variant of recurrent neural networks called long short-term memory, or LSTMs, come into play. Because here, this variant of recurrent neural networks actually has a memory cell that's able to preserve state over long periods of time. With that being said, let's dig in and try to understand this a bit more. The first thing you'll note here is that WL varies between layers, but is actually shared through time. Here, for the purposes of this presentation, I've omitted bias vectors for brevity. The inputs from the layer below in depth, right, so that's HTL minus 1, and before in time, which would be the one below it, are transformed and interact through an additive interaction before being squashed by the hyperbolic tangent. And an LSTM unit itself is defined at each time step t to be a collection of vectors in RD, where D is the memory dimension. The vectors here are I, O, and F for input, output, forget, and then you have U, which is the new memory cell, C, which is the final memory cell, and H, the hidden state. So the activation of the input, forget, and output gates is made possible by the sigmoid function, which keeps the entries of the gating vectors between 0 and 1. It's also very important for keeping the model differentiable. And also, I, O, and F control whether each memory cell is updated, it's reset to 0, or whether its local state is revealed. Now, the next vector, U, which is the new memory cell, is in R space, and it ranges between -1 and 1, and is used to additively modify the memory contents. Now, this additive interaction is a critical feature of the LSTM's design, because during backpropagation, some operation, all it does is that it distributes the gradients. So this allows the gradients on the memory cells to flow backwards through time uninterrupted for very long periods, which is exactly what we need. And it would only get disrupted with the multiplicative interaction of an active forget gate. Now, another thing that you'll be able to see here in the case of the LSTM is that there is a direct connection between the cell's previous state and its current state. So gradients can more easily backpropagate through cells without vanishing. So it really does solve the vanishing gradient problem. And because only the forget and input gates interact directly with the cell state, long-term dependencies can persist more easily through time and many unrollings. One last thing I'd like to note on this slide is that the cell state can be thought of in another way as well. The cell state at time t, for example, can be thought of as an encoded representation of the time series by time t. So the fact that it takes the previous output as an input means that each step input is used to continuously update the internal representation of the time series. So by the end, the output is the encoded representation of the entire time series up until that point. So we've discussed the sequential, and we've handled the sequential and structured component and characteristic of our data. What do we do about the hierarchical characteristic? For that, we jump to from recurrent neural networks. We've gone to LSTMs, and now we're going to make the leap to tree LSTMs, which have come in two variants. There are NRE tree LSTMs and child sum LSTMs. NRE LSTMs are ordered children indexed from 1 through n, where n is the branching factor, and they work much better with binarized constituency trees. Child sum networks are unordered, but they're summed anyway, and they're very well suited for high branching factor, which is exactly what we have. Now, to kind of see an overview of this, you can look at the green diagram, which is really what we're going for, right? That's the learning structure that, both from a time perspective and the data perspective, that we're going for. So both variants compose this hidden state from the input of the current time step plus the hidden state are arbitrarily many child units. That's why it outperforms all recurrent neural network and LSTM baselines on two tasks: semantic relatedness and sentiment classifications. Now, one of the key differences between the standard LSTM unit and the tree LSTM unit, regardless of the variant, is that the gating vectors and memory cell updates are dependent on the states of possibly many child nodes. Additionally, instead of a single forget gate, in the case of the tree LSTM unit, each child will have its own forget gate, which allows the tree LSTM unit to selectively incorporate information from each child, however it's necessary. So in a dependency tree application, the model can learn parameters wi such that the components of the input gate I have values close to 1 when a semantically important component of code is given as an input. So that would be like a class definition or a function definition, and values close to 0 where the input is relatively unimportant. So that would be the name of a class, Bob, Alice, whatever, or the name of a function. I hope you guys don't name your functions Bob and Alice, though. Now, since the child sum tree LSTM unit conditions components on the sum of child hidden states, it's really well suited for trees with a high branching factor or whose children are unordered. So it's a good choice for us specifically because the number of dependent nodes is going to be very highly variable, right? So from one code base to another, even from one file to another, the number of dependent child nodes is going to vary greatly. So yeah, this concludes kind of the representation preview of how we would go about solving this problem in this project. So that's where we ended up choosing tree LSTMs as a model. Now for the reconstruction bit, you want to really think of this. First of all, on the left-hand side, it's just a graphical representation of the code that gets built, reconstructed, on the right-hand side, right? So you can think of this in a way as rehydrating the tree by pouring memory and state from the top so that it flows throughout the tree all the way down to the leaf nodes. So specifically on the right, you can see code that is generated at each layer. So if you look at the very top, you see that at the start, you know that something follows the function definition, but you're not quite sure what it is. But by the time you get to the bottom of the tree, you have the full function construction. Now imagine this, a very simple example applied to a file, to many files, classes, and even entire libraries. The next very important component of this is thinking about loss, right? You need to be able to measure loss in any kind of learning system and be able to optimize on it. Now, the vanilla form of loss here is defined by looking at the output of the model, right? And comparing that with the original input, calculating the square loss of the difference. And this may seem very intuitive because I have something, I'm encoding it, reconstructing it, and it just makes sense. But it does open us to a rather problematic pathological state where you're not really learning anything. And here, what we're really afraid of is that there would be no compression in the hidden layer, and each hidden layer could copy a different input. So really, in such a case, there's no guarantee that the hidden units will extract meaningful structure. So instead of feeding x, the original input, we feed a noisy version of it. And this is achieved by basically putting the original input through some noise process and, in essence, creating a representation eventually that's robust to noise. Now, one thing that I want to note here is that the loss function, this new loss function, would then compare x hat at the top, right, the output, not to the corrupted data that we've created, but to the original data. And it learns from that over time. So in this in this way, we're forcing the autoencoder to use a variety of inputs and to try and learn about relationships between input values to be able to minimize loss instead of just copy pasting, right? Great. Finally, we have efficiency before we get started and the presentation's almost over. So the efficient batching of tree data is complicated by the need to have evaluated all of a node's children before we can evaluate the node itself. Now, to minimize the performance impact of this issue, we break the node evaluation process into steps such that at each step we evaluate all nodes for which all child nodes have been previously evaluated. And this allows us to evaluate multiple nodes with each torch operation increasing computation speeds by an order of magnitude over recursive approaches, which may theoretically at least seem better. But when you want to apply it, it's just simply unfeasible. It just never finishes, especially on large data sets. So as an example, if you look at this tree, on the first step of the tree calculation, we can evaluate nodes 1 and 3 in parallel because none of them have child nodes. And then at the second step, we're able to calculate node 2 because child node 3 was evaluated previously. And finally, we evaluate node 0, which depends on nodes 1 and 2. So doing this, we can reduce 4-node computation into 3 steps. And believe me when I say that bigger trees and bigger libraries that you're trying to autoencode will see much more massive performance gains when you go about it this way. I'd like to dig into this deeper, but we're running out of time. So, we know all this. We've made all these decisions. We're happy about them. How do we get to implementation? It all starts with preparing the data, right? So at the, we start with some Scala source code, right? Obviously, this is not a library. This is just literally a single line of Scala source code. We have some val sum equals a plus b. We want to extract and, convert this to a scalameta AST, which would look like that. And then finally, get it into an NRE tree, right? With a node where you have a token, right, for each node. And you have all these nodes. Now, I know it's not readable, but it's really meant to illustrate the number of nodes that we can have using scalameta ASTs. This transformation was done by 3 parts of code generation, which I've collapsed because even the code gen is very long, where we're generating the tree code, the param code, and finally generating that giant node. Finally, what actually comes out of the Scala side of this library is a JSON file, which we dump to Python dictionary, and then have the PyTorch LSTM library, tree LSTM library, use that as the input for the model. Great. So you dump the Python in. You dump the data into a Python dictionary. The first thing you want to do is basically create an embedding vector from the original token that we saw in just the previous slide. And this is how we go about doing that. And then you want to be able to get all the fields minus the token, so that you can look at all the nodes and be able to to train on that. And finally, once we have all of these components, we want to convert this tree to tensors for training. Now, some of the fields that you'll notice here is there's the token to IDX, which maps the token to some index, right? And token size, which is the number of unique tokens. Now, this is problematic because let's say I have a token continue, which says, I'm at the top of, I'm at the very top, and end, which is like the leaf node. Originally, if this gets indexed into, mapped into indices 5 and 6 respectively, that to me tells, 5 and 6 are very close. But I know that continue and end are actually very different, right? They have very different meanings. So instead, we use embeddings to embed them into that embedding space. Those numbers are chosen at random at the very start, and then optimized using stochastic gradient descent. So, yep. This is how we actually kick that process off that I just described, from going from embedding all the way to the feed-forward component. So we already saw how a tree is hydrated, but this is just a review of the reconstruction and decoding process as we implemented it. So from the tree LSTM encoding bit, you get the final hidden state and memory, and inject that into a linear LSTM, which generates a token of the root node. Examples of that would be continue and etc. And from that you get a new hidden state and memory, which is injected to a new LSTM, which exists for each child node. So our results here, this is literally generated just for a tiny bit of code. And it's one of the files, the JSON files that was generated. That's our results. I assumed the last time I did a presentation of this kind, people wanted to see the code results, and so I filmed it. But the MSE, the mean squared error, which is what we're using to calculate, accuracy in this case, is calculate error, sorry. This case is 0.05, which is really good. And we know that we're not having this identity problem. So there's that. For the future, here are some of the things that we've planned. We want to train the model on more code bases. We want to be able to use the model in industry. And use Scala bindings instead of PyTorch. Now, the last time I gave this talk, I said we would do this, but I haven't gotten around to that yet. As I said, I have a day job. And then we also want to be able to experiment with deeper layers to dig into edge cases, and also to extend the library beyond just autoencoders. Thank you guys very much, and I hope I made it just in time. Thank you.